Our next speaker is Kimberly Kowal Arcand from NASA Chandra X-ray Observatory. And Kimberly is going to speak about holding the cosmos in your hand, developing 3D data pipelines.
Good morning, everybody. Welcome. This is, let's see, a beautiful morning in New England. So I'm happy to be here with you all for the next few minutes. I'm going to talk a little bit about what we do with 3D models as far as establishing them in a pipeline in order to help promote inclusivity and accessibility in astronomy. So we are, I think, very fortunate to have a wealth of data in astronomy, and what we're looking at here on the slide now is just the electromagnetic spectrum. And of course, we have even more information than that available to us through multi-messenger astronomy as well. So gravitational waves, cosmic rays, neutrinos, etc. There is, with all of this availability of information, a number of ways that we can take that information and translate into something else. And that's what I'm hoping to spend the next few minutes just taking a look at. So, as mentioned, I work for the Chandra X-ray Observatory, which has been orbiting for over 21 years now. It's been really exciting to be a part of that project, and Chandra has just provided a wealth of information on the high energy universe. We're looking here at an image of Cassiopeia A, a supernova remnant that's a little over 10,000 light years away from Earth. And it is beautiful in X-ray light, of course, just a little bit of very lightly processed X-ray data. And then, of course, when we're working on our two-dimensional images, we can choose any number of ways to take that data and visualize it for a specific format. So, for example, this image is taking the X-ray data and color mapping it by chemical emission. So the iron, for example, is in purple, and the silicon and the sulfur, etc., and then overlaying it with Hubble optical data. And this image is one of my absolute favorites, and I love this target very much. Chandra has like over 2 million seconds worth of data on Cassiopeia A alone. But when you have better information, when you have that velocity information, you can essentially do these 3D models, as some of the speakers this morning or this afternoon, depending where you are, have been reviewing. This 3D model was sort of what started me down a very long path of visualizing beyond just 2D. It was work that was done by Tracy Delaney and her team back in 2009. And I guess going back a few speakers, it actually did use an interdisciplinary tool called astronomical medicine, which was spearheaded by Alyssa Goodman at Harvard at the time, that took brain imaging software from some local area hospitals in Boston and then adapted it for use in astronomy. And we worked with Tracy Delaney for this project, so to create this 3D model of Cassiopeia A using the Chandra X-ray data, but also infrared data from the Spitzer Space Telescope and optical data from ground-based telescopes as well. But it sort of just blew my mind as to the possibilities. I hadn't seen really anything like this back in 2009 yet. And since then, we've been able to take this 3D model and just provide many different outputs with this type of data. So one of the first things we did was learn how to 3D print. I had some colleagues at the Smithsonian Institution who were in the process of 3D scanning and 3D printing President Obama's head. And when I saw the result, I thought, well, you know, if they can do that, surely we can figure out how to 3D print this supernova remnant. And so we did, through some trial and errors, plenty of errors, but it was pretty successful. And it was just a really incredible project to work on. But we also wanted to see what more we could do with it. So we started working with powder printers to be able to see if we could keep that color information. So here again, you can see the iron is now in green. And by taking this image and then having the color mapped onto it, but then also having tactile information, you can take a 3D print that was once just kind of plain colored, single color. I don't know if you can see my screen. And then preserving the chemical emission information as well. But I also wanted to see what we could do beyond just 3D printing. So we brought it into virtual reality. This is a VR cave down at Brown University that I've been working with for the past maybe 4 years or so. And this is one of my students. And you can see she's got her headset on and she's exploring this supernova remnant in virtual reality, which is, again, fantastic to be able to do. We've since taken that and brought it into personal VR devices like Oculus Rift, or Oculus Quest and Oculus Go. Beyond just virtual reality, though, we've also taken this into augmented reality too. This is using the Microsoft HoloLens. And in this project, we were able to take the data and then build that supernova remnant interactively. So for example, I think you'll see it in a bit in this demo video, but our sample user here is taking each layer, the silicon, the sulfur, the iron, etc., and building it up layer by layer. So, in your office, in your school, you can build a supernova remnant of your own. However, what I wanted to also figure out how to do is to take this 3D model and bring it into other applications. So we created one augmented reality application that took 3D models like the Cassiopeia A1 and embedded it in a way that made it educational for younger students who hadn't had any sort of experience with 3D models before. So in this application, it takes the 3D model and then also applies sound. And by picking and choosing each layer, there are different sounds that are played. And again, the user is able to interact with the model. And you can see just a little bit of that on the right side, but I don't think I have the sound playing. Another way that we've taken this data is by using screen-based holograms, and especially during a pandemic, I'll just say screen-based holograms are incredibly useful. You can interact with this object by using the sensors that just detect motion, and so you can interact with a 3D environment without having to have anything on your hands or on your head, making it a very touchless way to interact with a 3D model, which again, has been very useful, unfortunately, during a pandemic. And then finally, as I mentioned a few slides ago, but didn't really get into too much detail with, one of the things that I was very interested in when we were working in our VR world was that if you're working in a VR world and you're creating an object or an experience with that VR space, if you do not have sight, that experience is going to be greatly unuseful for you. So what we've decided to do is to take sound essentially and map it to that spatial data. And most recently, we've also been able to take haptic information, so like the type of vibrational information you have on, for example, a smartphone, and attach it to that spatial information as well. So if you are blind or low vision, you can still experience that three-dimensional mapping of the exploded star by either incorporating the sound layer or the haptic or vibrational layer. And this version that I'm playing through now is just a two-dimensional data sonification. So the sound is mapped based on the intensity layers of the image itself, and it's not spatial. But since I couldn't play the spatial version, I thought I would just play that first. So all of these different versions are just, again, different kinds of translations, and taking that information and then bringing it into a particular kind of output or product based on the needs of the user. And all of this information that I've been talking about really is information that is, invisible to human eyes anyway. So being able to prioritize other senses or to be able to think about other ways of accessing that information has been really useful. I'm going to very briefly scan through a couple other objects that we've done this with. This was definitely not a one and done type of project for us. We were very interested in establishing these sorts of pipelines, because once you have the three-dimensional information, you can translate that into innumerable ways of understanding, of perceiving, of comprehending for the user. So Tycho supernova remnant was another really great object for us. For Chandra specifically, of course, Chandra is really great at supernova remnants because of its spatial resolution. Tycho supernova remnant's a bit farther away than Cassiopeia A, but still relatively nearby in the Milky Way. In this case, we were working with Arcand et al. And their 2019 paper, where they had created these simulations that were constrained by the observations of Tycho to create this sort of beautiful 3D print. And I don't know if you can see my camera. When it's green, it goes away in the screen, but there's a two-part model here where it's the ejecta and the shockwave. Another is Supernova 1987A, again, combining the visualization, which is a simulation but constrained by the X-ray observations. And again, another example of how very useful supernova remnants are in this world. Again, a really beautiful 3D print that we've been able to get of this. And I'm not showing the virtual reality for each of these, but we've also been able to bring these into virtual reality spaces, into holograms, into data sonifications, et cetera, like I showed previously for Cassiopeia. The Crab Nebula is another new one. Again, another example of a remnant. Thank you. And you can see we have a really lovely 3D print here showing this nested structure of the Pulsar Wind Nebula. And other types of objects as well. It's not just supernova remnants, of course, those are my favorites. And Chandra has such great data that it's hard not to make use of them. But V745 SCO is another one that's really cool. I don't know if you can see my 3D print here. And I do want to get to questions, so I'm going to just try to pop through some of this fast. Other teams, other collaborators like Stefan et al. From 2014 have the Homunculus Nebula for Beta Carina and Pillars of Creation, or M16. Again, this is from McLeod et al. From 2015. Many different examples of this. Here's another one of the Cosmic Web, which can't tell if you can see that. So what have we done with all of these 3D models? Well, one of the things that we've been doing is to create these 3D printed kits of 3D models, but also braille and tactile materials to work with students and lifelong learners who are either blind or low vision. And one of the really key things for us was to make sure that we incorporated the community during the development of the products. So it was sort of a first step for us just to learn how to 3D print and what to do with some of these models. But then the second step was getting our user input and being able to improve the models. So we have a paper, I don't think I listed it here, but it's at the end, from a couple years ago. We worked with students at the National Federation of the Blind's Youth Slam program. And one of the first models we showed was Cassiopeia, which is one of my favorites. And almost immediately the students just were asking, you know, well, we can't see inside and we can't access the inside. So can you just cut it in half? And it was just such a beautiful aha moment for me. Of course we could cut it in half. There's no reason why we can't. So we did cut Cassiopeia in half and applied little, magnets around the perimeter so that you could put it back into one piece. But this way that people who are blind or low vision have access to the internal data as well. But like pretty much anything that I've talked about here today with all of these different outputs from these 3D models, anytime we take a 3D model into some form and then work with a community or a group to improve it, it improves it for all users as well. The data sonifications, for example, have turned into some of the most popular material that we've ever done. These 3D models, these 3D prints, we have used just in all sorts of places, and the response to them have been pretty amazing. So having all of that user input when we are creating a data sonification, when we're working on virtual reality that includes sound and haptic technology, it's not just our team saying this is what we want to do, but it really is incorporating the viewpoints of the end user to be able to understand what it is they need to access from that information and how it is that they can get the most lemon juice out of those lemons. So I did not have time to go into some of the geophysical models, but we do have a paper that was recently accepted and will be coming out soon that goes into some of this in greater detail if you're interested. And also my co-author Megan Watsky and I are writing a book on this topic. So there will be more coming. I think I'm just about at the end and I'd really like to have time for questions, but all of these models that I've been talking about, we also have linked from the various web pages that I've listed under the reference URLs. So please do feel free to take a look at some of those. And if you have any questions or whatever, let me know. The fake clapping is wonderful.
It's better than the clapping that happens on Zoom when everyone forgets to unmute.
It is.
Very much, Kimberly. That's incredible. Do you have any questions? I know I have a question. I'd like a radio galaxy printed, or a few.
A radar galaxy would be great. And we do, I should say, there are other methods and other ways of doing, for example, 3D prints. So there are techniques that Dr. Nicholas Bond at the UK and his team are doing, where you're taking the intensity information and mapping that into a 3D print versus having to have like a full 3D model. So if you don't have like complete 3D data, there are absolutely ways to make 3D prints of them and to do some of these other visualization or representation outputs as well. I didn't get to talk about those, but I'd be happy to talk about that on Discord.
Great, great. I will definitely follow up on that. Any more questions? If not, then thanks to Kimberly again.